So hopefully at this point you guys have mastered the art of covalent bonding and single bonds. Same rules apply, but sometimes things get a little bit more difficult. Now we're sharing electrons. This is covalent bonding. This is two nonmetals or a nonmetal and hydrogen. But it is possible for atoms to share more than one pair. This is kind of common sense here right at the beginning. If they share two pair of electrons, it's called a double bond. Every now and then things make sense. If they share three pairs, it's called a triple bond. And because everybody is going for that octet, trying to achieve those 8 electrons, you're not going to see anything really bigger than this. You're not going to see a quadruple. You're not going to see a quintuple. Nothing like that. So here's what this looks like and how you know that you might have double bonding on your hands. Let's look at carbon dioxide. Carbon dioxide, CO2. So we're going to stick to the rules we set before. We said if you have carbon or if you have something that there's only one of, stick it in the middle. We always start there. Then, you've mastered this. We're going to fill in our oxygens, 2, 3, 4, 5, 6, and then fill in our oxygen, 1, 2, 3, 4, 5, 6. So this is the point at which you start to realize, wait a minute, I have a problem. Everything you did before, when you put the pieces together, everybody was stable. But if you do a quick count, this oxygen right here has 7. This carbon has 6. This oxygen has 7. Nobody's stable. So that's when your brain should start kicking in that maybe there is a double bond happening here. For a double bond to work, almost all of the time, and we'll talk about the exceptions later, but for now, all of the time, you're going to have one from one atom, one from another, just like you do with a single bond. So what we're going to do here is we're going to take this electron from carbon and move him in here, and this electron from oxygen and move him in here. And when we do that, okay, I'll erase this guy, I'll erase this guy. When we put them in there, now we are sharing more than one pair of electrons. Okay, so now there are 2 electrons being shared. That is what we call a double bond. It also changes it, so now this oxygen has 8. He's stable. But again, now I'm looking at my carbon, and if I look at my numbers again, that carbon still only has 7. So one clue that you can get there's double bonding that's going to be happening is looking at the number of electrons. Another clue is if you have singles left, okay? There's a single here, there's a single here. Shouldn't happen if everybody's nice and stable. So we're going to try again to form a double bond. You also have to think logic, okay? I can't take this oxygen electron and whip him over here. That's not possible. He can only go to a different side of the oxygen he's already on. So if I move him in there and I move this carbon in there, I'm not really taking anybody away from where they belong. I'm just putting them on a different side of the atom they're already on. So if I erase these guys, now I start counting electrons again. This carbon has 8, okay? This oxygen has 8, and everybody's happy. If I look at this in terms of a structural formula, what happens is my double bond looks like an equal sign, okay? It's 2 pairs of electrons being shared, and that's how I'm going to represent it. So there's really no trick to know, oh, hey, look at this. This is a double bond. There are a couple, but they can get pretty complicated. My best advice for you guys is to really just look, okay, at your dot diagram as you're trying to put the puzzle pieces together and look for those clues. Look for single electrons that are left. Look for not having 8, even though all the pieces are in. Okay, let's look at a triple bond real quick. Carbon monoxide is actually going to be a triple bond. Now, I'm going to tell you that, but now I'll show you how I know that. Actually, sorry about that. Instead of looking at carbon monoxide, let me switch gears for a second. Let's look at a different one. Okay, let's look at HCN. And I'll come back later to why I did not want to do carbon monoxide quite yet. If I look at HCN and I start putting my pieces together, there's my carbon. We know he's going in the middle. Okay, keep following my rules. I'll put my nitrogen on next. I got my shared pair holding them together. Okay, and now I'm going to go ahead and put my hydrogen over here. So all my pieces are in, but not everybody's stable. The one thing that I do notice is this hydrogen is stable. He has 2 electrons. So I don't want to add anything right there. I want to leave that the way it is because hydrogen can't have more than 2. So I'm going to start looking at a multiple bond between the carbon and the nitrogen. So if I pull this guy in and that guy in. Okay, let me move these guys around, erase them. Pencil is your friend when it comes to covalent bonding. Now I've got a nice double bond between my carbon and nitrogen. But if I start counting electrons, this carbon has 7. Okay, that nitrogen has 7. That's not what I want. So I can make yet another multiple bond by moving those guys in. So I'll move that one from carbon. I'll move that one from nitrogen. I'll erase where the original came from. And now when I count, okay, my nitrogen now has 8. My carbon now has 8. Because remember, the ones between them, each one gets to count. When I look at the structural formula, a triple bond is an equal sign and then some. Okay, it's 3 lines. I know in my dots I have them kind of going vertically. It's really up to how it works for you in terms of a dot diagram. You could have done this dot diagram with the 3 here and then the 3 here. It's really all the same. But with a structural formula, it needs to be done like this. Don't turn your lines any other way. So these multiple bonds take a little bit of practice, and it's something you have to keep an eye on. Now, going ahead and adding to this, there are exceptions. Of course there are exceptions. Not everything follows the rules just like it's supposed to. So there's 2 different exceptions that I want to show you. One is there are some elements that have an odd number of valence that do a very strange thing. They buck the whole need of 8. For example, if I look at BF3, okay, boron trifluoride. Boron has 3 valence electrons. So when I put my fluorines on, again, following the rules, put that one there, I'll put that one there, okay, I'll put that one there. Everybody's on there, there's all the pieces of the puzzle, fluorines are all happy, fluorines are all stable. The problem is, that boron only has 6 on it, but there's nothing left. I can't do a multiple bond, I don't have any extra electrons. This is literally everything I've got. Believe it or not, boron is happy just like that. There are occasions with things, boron is a big one, where boron is stable with only 6 electrons. He is an exception to the rule. Another one that's very similar to this is phosphorus. Now, phosphorus and arsenic are both famous for doing this. So let's look at PCl5. Put my phosphorus in the middle. Again, there's one of them. He has 5 valence electrons. And then I start adding my chlorines. 2, 3, 4. He has 7. He has 7. One more. He has 7. And you're thinking, sweet, everybody's stable, everybody's happy. Problem is, that's only 3 chlorines, and that says I'm supposed to be putting on 5. So where in the world can I put them? There is nowhere to put them if I'm sticking with the octet rule. But if I buck the octet rule, what you can see is that I can add a chlorine to each one of these top valence electrons. Now, that means each one of these chlorines is good to go. They've got 8 valence. Sorry about that. But this this phosphorus right here, count them, he has 10, okay? And he's happy that way. So there are a couple exceptions to this pattern. PCl5 is one you've got to look at, and then boron is another one you're definitely going to have to be aware of, because we will definitely see this with boron. Another exception that you'll see, this is number 2, is something called coordinate covalent bonding. Now this is really actually not in the scope of our class. This is a little something extra that I just want to show you. Coordinate covalent bonding is what happens with carbon monoxide. It's why I stopped myself when I was going to show you that with triple bonding earlier. When I put my carbon and my oxygen together, okay, to make carbon monoxide, 2, 3, 4, 5, 6, I start by making my double bond. So I'll move 1 electron in there, and then 1 from oxygen in there, and I'll erase both of those guys. But when I get to this point here, I have a problem. I don't have any more singles from oxygen that I can actually move in there. Okay? There's no way to do the bonding the way we have. So something very strange happens here. This guy will come over and pair up with this guy, and these two will actually go down into the middle here. So what we end up with is a very special kind of triple bond. Okay, here's my carbon, here's my oxygen, where part of the bond is made up just with things from oxygen. So it is still a triple bond, okay? I still draw it just like I would a triple bond, but what happens is we have like a special notation for it. You'll see an arrow on one of the triple bond signs to show you that the electrons came in that pair right there from the oxygen. Now, this is not something I expect you to do, not at all. It's just an exception that I want you to know is out there and something I want you to be able to recognize if you see that kind of notation.